Hi, I am Dr. Nicholas Samut, and today we're going to look at sinusoidal oscillator principles. This is part of MNE 3701, Oscillators and Filters course. What are oscillators? Well, we have seen already that certain circuits are made to be stable using certain principles like negative feedback, for example. However, a sinusoidal oscillator is a circuit that is basically designed to intentionally be unstable. Basically, an oscillator is a circuit that produces a periodic waveform in its output with no signal input, and as input it only has a DC power supply. So basically, a sinusoidal oscillator is a source in itself. A repetitive input signal is not required, except maybe to synchronize the oscillator in some way, but it works just by having a DC power supply, and as an output it gives you a sinusoidal waveform. So basically it's converting the electrical energy from the DC power supply into a periodic signal output. Sinusoidal feedback oscillators. So we're going to look at this particular design where we have an oscillator based on the principle of sinusoidal feedback, and a portion of the output signal in this type of configuration is fed back into the output. In fact, you can see this in the diagram on the left, where the output is being fed back through an attenuation and phase shift circuit and fed back into the amplifier input. We see that the signal has no phase shift when it is fed back, and the signal that is fed back reinforces the output signal. So in this case, it is known as positive feedback, not negative feedback. Therefore, after the oscillations are started, the loop gain has to, however, be maintained to 1 to maintain oscillations. Otherwise, if it is larger than 1, the output signal will continue to increase and increase and increase until you get to your power supply limit, and you would not have the type of oscillations that you require. So basically, for an oscillator, you need to feed back the output signal, have that form of instability through positive feedback. You make sure that your phase shift is not changed, and like that you also maintain the loop gain equal to 1, so that then you reach stability of oscillations. We will see this in more detail. Let's look at positive feedback in some more detail. In positive feedback, there is no externally applied input signal. You also have a portion of the output voltage of an amplifier fed back into the input, and there is no phase shift. The feedback signal reinforces the output signal, and a loop is created in which the signal sustains itself. So therefore a continuous sinusoidal output is created, and the oscillations generated are through regenerative feedback. This you can see very clearly in the diagram on the left, where the output signal of the non-inverting amplifier is fed into a feedback circuit and then fed back in the input of the amplifier. Moving on to negative feedback, some amplifiers shift the phase by 180 degrees, and as soon as you see that, you realize immediately that negative feedback is being used, contrary to positive feedback that we have seen earlier. So in this case, an inverting amplifier is required in the feedback loop to provide this 180-degree phase shift. And there would therefore not be any resultant phase shift, and the oscillations are sustained. Now let's go back to oscillators. For an oscillator to actually function properly, 2 conditions would be required. The first condition is known as regenerative feedback, which you can see on the left, whereby the phase shift around the loop is equal to 0 degrees, or 360 degrees for that matter, but ideally a phase shift of 0 degrees. So in this case, the phase of the output is equal to the phase of the feedback that is inputted again into the input of the amplifier. On the right, we've got the second criterion, known as the Barkhausen criterion, whereby we have to make sure that we maintain the closed loop gain equal to 1. So we first have to start up with a gain that is larger than 1, and then until you reach a gain that is 1, you make sure that the gain stops at that point. Now let's look closer at the Barkhausen criteria. Over here we've got a diagram showing this principle using negative feedback, where V out on V in is equal to the gain all over 1 plus the gain multiplied by the attenuation of the feedback circuit. Therefore, the oscillation results when the feedback system is not able to find a stable state because its transfer function is not satisfied. And the system becomes unstable when 1 plus AB is equal to 0. So when AB equals minus 1 and the angle is minus 180. So in a positive feedback system, the gain is equal to 1 and the phase shift is equal to 0. So basically you need to have a closed loop gain of 1, an amplifier open loop gain of AV, and an attenuation in the feedback loop of B. A loop gain greater than 1 will therefore rapidly cause the output to saturate as both peaks of the waveform. Now, to avoid this, some form of gain control must be used to keep the loop gain exactly at 1 once oscillations have started. So, example, if you have an attenuation of 0.01 and then amplifier gain, the amplifier gain must be exactly 100. If it is less, the oscillations will die out. But if it is more, the oscillations will cause the oscillator to limit both peaks of the wave. And here we're seeing this graphically. So on the top left, you see that if you've got an attenuation B of 0.005 and a gain of 100, you will see that the oscillations will slowly die out. At the bottom left, however, if you see that you've got a gain that is larger than 1, because AV is 100 and the attenuation B is 0.1, then the oscillations will start to increase and increase and increase until they reach the power supply limit and they start to clip. However, if you've got a gain equal to 1, then AV is equal to 100 and B, the attenuation, is equal to 0.01. Now if we look at the phase shift in the oscillator, the 180 degrees phase shift in the equation AB equals 1 with an angle of minus 180 degrees, this is introduced with active and passive components. If the shift is ideally made dependent on passive components because they are accurate and drift-free, okay, the phase shift also uses active components when it is minimized because it varies with temperature, has a wide initial tolerance, and is device dependent. Also note that amplifiers are selected such that they contribute little or no phase shift at the oscillation frequency. Right? The op-amp oscillators are also constrained to relatively low frequencies. Also note that a single pole RL or RC circuit contributes up to 90 degrees phase shift per pole. We will see this in more detail at a later stage. In an LC circuit, which has two poles, it hence contributes up to about 180 degrees per pole pair. Now, if you also look at LC and LR oscillators that are not considered, because they are low frequency inductors and they are expensive, heavy, bulky, and they're very non-ideal. Yeah? We also note that LC oscillators are used in higher frequencies, whilst multiple RC sections are used in lower frequencies. And the range of change of phase with frequency, defined by the W, by the omega, determines the frequency stability. Now, if we look closer at the phase shift of an oscillator, you will see that if you've got single RC sections, it is not enough to get the 180 degree phase shift that is required. So we need at least 2 to get the frequency of oscillation that is dependent upon the change in phase at the point where the phase shift is 180. So you therefore need a tight specification where you have a large phase shift in the phi for a small change in frequency the omega at 180 degrees, and this gives your oscillator much more precision and much more stability. So d phi by the omega for two RC sections is, however, even though it is possible, it is unacceptably low, and it results in poor frequency stability. So usually 4 RC sections are used to increase the frequency stability. And this is because op-amps come in quad packages, and one can have 4 sine waves of 45 degrees to obtain sine, cosine, and quadrature sine waves. We also mentioned the Barkhausen criteria. However, for us to get a gain of 1, we need to at least start up the circuit. So we need to start the oscillations in the beginning, and then when they reach stability, we need to change the gain so that it is equal to 1. So in the beginning, we have to make a gain that is larger than 1. And then as we reach stability, we have to make sure that we get a closed loop gain equal to 1. So basically, for oscillation to begin, the voltage gain around the positive feedback loop must be greater than 1 so that the amplitude of the output can build up to a desired level. And the gain must then decrease to 1 so that the output stays at the desired level and the oscillation is sustained. You might ask, however, but how does the oscillation actually start? Well, if the oscillator is initially off and there are no output voltage, you first need to do that through thermally produced broadband noise in the components or from power supply turn on transits. Alright, so basically it happens normally because of noise. However, sometimes you may also try to induce it with a pulse, for example. This can be the startup pulse, for example, in your circuit. Also note that the feedback circuit permits only a voltage with a frequency equal to the selected oscillation frequency to appear in the phase of the amplifier's input. Right? So even so, your noise would need to include many frequencies. Normally, white noise is ideal for this situation. The initial voltage is amplified and continually reinforced, resulting in a build-up of the output voltage.